Hello, 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 and welcome, normal physicists, to our delightful third problem in the second forces and free body diagram problem set. We've got, in this problem, Blorgus 16, a planet in the Beep Darp system. Both of these are names I made up, as you can probably tell by them being stupid. So the Beep Darp system's named after a star called Beep Darp, obviously. Beep Darp is a red giant with an enormous mass of 1.6 times 10 to the 31st kilograms. So the mass of our star, that's M, I'm going to call this MS for the mass of our star, is 1.6 times 10 to the 31st kilograms. Big number. That's a 1-6 with 30 zeros after it. In scientific notation. So we've got a red giant with a big mass in the center. This is Beep Darp. I'm going to label it S for star. Big mass in the center. So Blorgus 16 is a terrestrial planet, not too dissimilar in size from Venus, with a mass of 9 times 10 to the 29th kilograms. So we're going to go MP for mass of our planet. That one is 9 times 10 to the 29th. Or 24th, excuse me. 9 times 10 to the 24th. So this is also an enormous amount of mass, obviously, because it's a planet. Obviously, since this is a planet, high number, it's still about 10 million times smaller than Beep Darp, which is actually pretty accurate for a planet orbiting a star. That's why the sun is the center of the mass and the solar system is because it's much heavier. So there's our star. Here is our planet, P. Now, we know that the gravitational constant G is 6.7 times 10 to the negative 11th. And again, that's just from the problem here. Hoop and hoop and hoop. Right? Mass of Beep Darp, the star, MS. Mass of Blorgus 16, the planet, MP. Gravitational constant, G. Makes sense. So, we also know that Blorgus 16 has a tangential velocity of 41,000 meters per second. So, velocity is 41,000 meters per second. Oh, and that's in kilograms, that's in kilograms. Okay, so our planet is moving with a tangential velocity of 41,000 meters per second. Question, we've got a planet. It's in an orbit. What kind of orbit is it in? Circular. All planets move in circular orbits. So, that's cool. Let's take a look at what we've got going on here. So, looking at my equation sheet and reference guide, let's take a look at our checklist. Anything we can ignore? Not really. Frictional force, normal force, gravitational force. We're dealing with planets in the atmosphere, or in the solar system, not in the atmosphere. We're dealing with planets in the solar system, so gravitational force is not an object being falling down to the ground, right? It's just a planet that has its own gravitational field, so no. Normal force, nothing's pushing up against nothing. Frictional force, nothing's rubbing up against anything. So this whole bit, we'll ignore that. Force of drag, are we moving through a fluid? There's no air in space, so no. Spring force, nothing is being stretched, so no. FC, centripetal and centrifugal force, is this object moving in a circle? We've got a circular orbit, so yes. We'll have FC. Let's see. Next, FG. Universal gravitational force. Are these objects incredibly heavy, like the size of planets? Absolutely yes. So we've got F capital G. Then we've got pressure force, buoyant force, pressure being split over an area, no. Buoyant force, object filled with a pressure and submersion of fluid, no. Okay, no problems there. So we've got centripetal force and gravitational force. We know that the centripetal force is going to point into the center. And we also know we have centrifugal force. which is acting on this planet, pointing out. These two are equal and opposite. And we have a gravitational force pointing in as well. Gravitational forces point between heavy objects, right? So our gravitational force is pulling between the planet and the star. FG is going to act between heavy objects. So this planet and this star are pulling towards each other. It goes in like this. Now, centripetal force is always caused by another force. In this case, it would make sense that our centripetal force that points into the center is equal to our gravitational force. They're the same, right? The gravitational force is the reason this thing is staying in a circle. Centripetal force is a thing moving in a circle, right? It comes from a thing moving in a circle, and it's always caused by another force. When I'm spinning a yo-yo around in a circle, it's the tension in the string. When I'm banking a NASCAR car off of a turn, it's the wall, right? The normal force of the wall. In this case, our centripetal force is caused by gravity. So these two are going to be equal. So we could say FC equals FG. Now, let's take a look at our equation sheet once again and figure out what these are. So we've got FC, that is the centripetal force, and that is going to be equal to mv squared over r. So FC here is mv squared over r. And now, in centripetal force, the mass you're referring to is the mass of the moving object, which in this case is the planet. So I'm going to make a little note that that's MP and not MS, right? It's mass of the planet, not mass of the star. So then, Fg, our force of gravity, we can get from our equation sheet as well. It is Fg right here. So that's capital G, M1, M2 over R. Capital G, M1, M2 over R squared. Excuse me. I don't know why that was misprinted on my equation sheet. I will make sure to fix that on the digital version of this that you guys have, if that problem is with all of them and not just with the one that I have here. But yeah, this R is actually squared in the gravity part. So, like I said, that is G times M1 times M2. In this case, we're like M1 and M2 just refer to the mass of the objects. I called them MP and MS for mass of the planet and mass of the star. The order doesn't matter because they're just getting multiplied, and then that's divided by R squared. Okay, cool. So now, the easy part is just math. So let's go ahead and say, all right, this one, MP, mass of the planet, we have that up here. That is 9 times 10 to the 24th. V squared, V is 41,000. Over R. R is the distance between them, which is what we're trying to find, right? How far apart are the two bodies? We're looking for R. So then, 9 times 10 to the 24th times 41,000 squared divided by R, which we're looking for, equals capital G, which is 6.7 times 10 to the negative 11th power. Problem tells us that. It's also a constant on our equation sheet. MS, mass of the star, is 1.6 times 10 to the 31st. And then MP is 9 times 10 to the 24th kilograms. And then that's over R squared. Now notice, this R and this R are the same, and they should be. They both represent how far from the center of the circle this object is, right? This R represents how far from the center of the circle. This R represents how far apart our two planets are. That R is the same, right? That distance is the same. We're talking about the same thing. So this R and this R are the same, meaning we can look for both of them. And we'll get our answer. So, algebra, whatever you do to one side, you can do to the, or you have to do to the other. A good way to get these R's together, just multiply both of these by R. That'll cancel here, and give us 9 times 10 to the 24th times 41,000 squared equals 6.7 times 10 to the negative 11th times 1.6 times 10 to the 31st times 9 times 10 to the 24th, and that's over R. Okay, so let's go ahead and get this into a conformation where our numbers are less enormous and gross. So let's see. That's 9. The way my calculator deals with this is E. 9E 10 to the 24th, 24, boop, times, parentheses, 41,000 squared, boop. It gives us 1.5129 times 10 to the 34th. I'm just going to call that 1.5. That sounds fine to me. So we'll say 1.5 times 10 to the 34th is this side of the equal sign. And then over here, we've got this times this times this. We'll go ahead and do that as well. 6.7 times 10 to the negative 11th times, put this in parentheses just to be safe, 1.6 times 10 to the 31st gives us this, and then times again 9 times 10 to the 24th. Okay, so this times this times this gives us 9.648. I'm going to call that 9.6 times 10 to the 45th. 9.6 times 10 to the 45th power, and then that's over r. So solving this for r should be pretty easy. We want r on both sides, multiply by r, boop, boop. We get 1.5 times 10 to the 34th power. R equals 9.6 times 10 to the 45th. Divide by 1.5 times 10 to the 34th. Divide by 1.5 times 10 to the 34th. 9.6 times 10 to the 45th power is what that is. Divided by 1.5 times 10 to the 34th power. Boop. And we get 6.4 times 10 to the 11th. So R equals 6.4 times 10 to the 11th power meters. And I chose pretty accurate numbers for this problem. I chose numbers that that were close enough to values from our solar system. So this is roughly, how far a planet like this would be from a star like this, right? So this R here, this distance is 6.4 times 10 to the 11th meters. That is about right for a planet in orbit. Likewise, something times 10 to the 31st, pretty accurate for a star. Something times 10 to the 24th, pretty accurate for a planet. And then 41,000 meters per second is a velocity for a orbiting planet, pretty accurate as well. So yeah, this one hopefully was not so bad. The main thing you got to remember for this is that your centripetal force is always another force, right? The force that's keeping your thing in a circle is always attributed to some other force. Sometimes it's tension, normal force, gravity, whatever. Usually it'll be pretty straightforward to figure out which one, though, just based on the situation. But your centripetal force and your gravity are equal here, so you can set them equal, do some math, get this as R. So hopefully this is helpful for you guys. I will see you again in the next one.